Yes, okay, thank you reminding. Yeah, it is on. Okay, so within a 16-bit, all bits, every bit, so 16-bit register. So every bit is not, I mean, is not important, or all bits are not active. I mean, it's only 9. So CF means carry flag. CF means carry flag, and then PF means parity flag, and then AF means auxiliary carry flag, and ZF means ZF means zero flag, and then SF is sign flag. So these 5 flag. So here is lower 8 bit. Okay, here is lower 8 bit. Out of lower 8 bit, five bits are active. They are called this thing. Okay, and there are other bits, other 3 bits. They are it is called U. So U is for undefined. Is for undefined. So I mean, it's not. Yeah, it has no value. Okay, so it is not a issue. Okay, so and then in higher 8 bit, it has 4 flags: TF for trap flag, IF for interrupt flag, DF for directional flag, and OF is called overflow flag. So 4 flags. And other higher 4 bits, they are reserved. So this is also not a point of interest. So this 5 plus this OF, overflow flag, they are called, I mean, status flags. And these 3 flags, TF, DF, and IF, they are called control flags. So what actually, and now we see that these bits, they are either 1 or 0, set or reset. Set means 1, reset means 0. After doing, I mean, microprocessor, when it performs ALU, arithmetic logic unit, within an execution unit, ALU, so once it perform any arithmetic operation or logical operation, so after the operation or after the result, the bits, these flag bits, they either set or reset. So let us see when actually they are set and when they are reset. So first of all, carry flag. So carry flag is set if there is a carry out or borrow in for the most significant bit of the result during the execution of instruction. Otherwise, it is reset. So what does it mean? So let's see. 1 0 1 1. Okay, now if you look at it, for example, we have a 2 number. If you add them together, add them together, so what will happen? So it will be like 1 1 1 1 1 1 1, and then 1 1 is 2. 2 means 0 and 1. So 1 is carry out. Okay, so MSB bit, there is a carry out happened in the MSB bit. Is it okay? So because 8-bit number, so for 8-bit number, this one is carry out, because this one is not within a 8-bit. It becomes out of 8-bit. So if there is any carry out or borrowing happens during the subtraction case. Okay, let's see an example. Like for example, yeah, this one is also, we can, if we if we do the, okay, again let me check. Okay, so a small number, okay, for example 4-bit 1 0 0 0 0. So this is 8, right? And if we have a number, if a 10 is okay, sorry, 1 1 0 1 1 1 1 0. So if, for example 4-bit number, so it's the same way like 8-bit or 16-bit, doesn't matter. So if you do the subtraction, what will happen? Do the subtraction. So 7 minus 10, so definitely it is minus 3. So that means if the bigger number is subtracted from the lower number, so there will be a borrowing happen. Borrowing in the MSB bit. How it happened? Like 1 minus 0 is 1. Then 1 minus 1 is 0. And 1 minus 0 is 1. And then 0 minus 1. So 0, it's not possible. We need a borrow. So we take a borrow. So borrow, we take a borrow here and put it here. So it becomes 1 0. Okay, it becomes 1 0. So 1 0 means 2. 2 minus 1 is now 1. So that means the result is 1 1 0 1, and there is a borrow in happen. So carry out or borrow in the MSB bit. So if it is the cases, then it is the case, then carry flag is set. Is it clear? So it can happen if we add two number, and if MSB bit, so it becomes out of range. I mean, there is an extra one. If the result becomes out of range, that means it is carry out. Or if we do the subtraction, there is a borrowing happen on the MSB bit, then it is also case that carry flag is set. Is that okay? Yeah. So look at here, this result. Actually, the result is minus 3. But if we look at this number 1101, this is not 3. It becomes like what? 1101 is 1010 110. Okay, so look at here, this one, because it's a signed number. If it is a signed number, so this one, looking this one, it means it is a negative number. So how can we get the magnitude of this number? So make a ones complement first. So 0 0 1 0, and then add 1. So it becomes 0 0 1 1. So it is 3. So that means this one is looking this MSB bit, it is a negative number, and then getting the twice complement from here, we'll get the amplitude. So it is 3. So it is minus 3. All right. Is it okay? I think this is basic about the number system, but I mean, just review. Okay, so carry flag. So now it is clear, I think. If you have a confusion, so let me know. If the carry flag is set, if there is a carry out or borrow in happen for the most significant bit of the result. Okay, this is called, otherwise it reset. Okay, what about the parity flag? Parity flag is say if the result produced by the instruction has an even parity, like for example 8-bit 1 byte 1 0 1 1 0 0 1 1. So this is the result. Okay, so you look at here, how many 1 here? 1 2 3 4 5. So 5 1, so it is an odd number. Yeah, so odd parity is called the odd parity. And if we have a even number of ones, then it is called the even parity. So for the even parity, even number of bits at one logic level, that means even for even parity, parity flag is set. Parity flag is set if there is an even parity, and if the parity is odd, then it is reset. So if we know the set, otherwise reset. That's it. So this is called the parity flag. What about the auxiliary carry flag? Auxiliary, we know the carry flag. What about the auxiliary carry flag? So auxiliary carry flag, it's about the, look at, okay, so let's see the example again for this one. 1 0 0 1 1 1 0 1, and then 0 0 1 0 1 0 0 1. For example, we have a two number. Okay, just for an example, we want to add them together. So what will happen? Okay, before that, we know that this is called 4-bit together is called a nibble. So lower nibble is called this one, right? This 4-bit here is lower nibble, and higher 4-bit is called higher nibble. So if we now add them together, so 1 plus 1 is 2. 2 means 0, 1 carry. Then 0 plus 0 is 0, carry 1, so it becomes 1. And then 1 plus 0 is 1. Okay, and 1 1, it is 2. 2 means 0, we have a carry 1. So look at here, 1 carry is carry out happen from lower nibble to the higher nibble. All right. So if it is the cases during the addition cases, if there is a carry out happen from lower nibble to higher nibble, or during the subtraction case, borrow in happen from lower nibble to higher nibble, at lower nibble from higher nibble, so then auxiliary carry flag is set. Is it okay? Do you understand it now? Yeah, so it happened if like so let's see the statement here. AF flag, auxiliary flag, is set if there is a carry out from lower nibble into the higher nibble, carry out, or borrow in from higher nibble into the lower nibble of the lower byte of 16-bit words of the lower byte of, so and I think this is enough. So into the lower nibble, yeah, then it is set. Otherwise reset. But it's not necessary for 16-bit word. It's for 8-bit also. It can 8-bit, say 8-bit or 16-bit. Yeah, what? So AP. Otherwise auxiliary flag is reset. Do you have any question here? No, all good. Okay, then zero flag. Zero flag is very simple. If the result is 0, then zero flag is set. For example, we do the subtraction like a minus b. If b is equal to a, then result is 0, right? So if the result is 0, then zero flag is set. Otherwise reset. Okay. Now about the sign flag. Sign flag is actually, it looks the MSB bit. I said that for the sign number, MSB bit actually it represents the sign. So simple thing is, if MSB bit is 1, then sign flag is 1. So MSB bit of the result is copied into the sign flag. That's it. What about the overflow flag? So overflow flag, actually, this is the tricky thing. Overflow flag, again number 5. Okay, sign flag. So sign flag is actually, it looks at the MSB bit. For example, the outcome, I mean the result is 1 0 0 1 0 0 1 1. For this is the result. So it looks at the MSB bit. This is the MSB bit, most significant bit. So if it is 1, it means sign flag is 1. If it is 0, then sign flag is 0. That's it. So MSB of the result is copied into the sign flag. Yes, and we also know that for the sign number, MSB bit represent the sign. If it is 1, it means it is a negative number, right? If it is 0, it means the positive number. So that's the thing. So sign flag actually, it is the same as the MSB bit of the result. If it is 0, then sign flag is 0. If it is 1, then sign flag 1. Okay, now we saw overflow flag. It is a little bit tricky. So overflow flag actually, it is the very kind of similar to the carry flag. So overflow flag is, it is I mean, when it actually related to the sign number. If for the sign number, if we have a sign number and negative number, sign number, and it is negative number, then actually overflow flag is a concern. So what does it mean? Okay, so right now I think when can I give you the example? Let's see. Actually, we will discuss the details in another chapter about with an example. So just right now, just just to know that when the overflow flag is said, it indicates that the signed result is out of range. Signed result is out of range. So it happens like, as you know, like during the carry flag, I give you the example. If the we have a carry out. Range means, like for example, we add 2 number. Okay, so they are 8-bit number, but result doesn't the result is now out of 8-bit number. Okay, so this means out of range. Like for example, 1 0 1 1 0. Okay, just 4-bit. Keep the look at the 4-bit 1 1 0 0. If we add them together, for example, so 4-bit number, our numbers are 4-bit. So 1 1 1 and then 0 and 1 is carry out, right? 1 is carry out. So this is out of range. This is like a example of out of range. So this kind of, because 5-bit because 4-bit, actually our numbers are 4-bit. So but if it is result is not within a 4-bit result, it is just an example, similar like 8-bit. If numbers are 8-bit but results becomes out of 8-bit, so it is called the out of range. So but these cases actually we discuss in carry flag cases. But here, what is the difference with carry flag with overflow flag, between carry flag and overflow flag? It is kind of similar. If does, but here it is said that if it is a signed result, if indicates that the signed result is out of range. So signed result means, okay, just I'm not, I mean, the example, actually we have some example in another chapter. So I'm just telling you now that if the results are negative number, simple thing is, if our it is similar like carry flag, but if the cases are with negative number, then overflow flag is similar like carry flag. So during the carry flag, if there is a carry out happen from the MSB bit, it is one of the cases. That one is also same like here overflow flag. If the numbers are signed number, if the numbers are signed number, then this is, or if the numbers are negative number. Okay, so we will discuss it later in another chapter with an example, then it will be clear, because it's on another chapter, I have to switch there. Okay, now it's about the overflow flag, then it's about the interrupt flag. What is called what does it mean? So this bit is set to enable or reset or clear to disable the external interrupt. You know, interrupt is like kind of disturb. I interrupt. Like if you, for example, I am delivering lecture, I am doing something on laptop, but if I press the power button, what happen? It will, or restart button, it will go for a restart. Okay, it will do the all the things. So that means it is like an interrupt. This interrupt, it is also external interrupt signal. So this is just an example. There may be different kind of interrupt request, like a disturb request, or like something is going on, but some request is coming to do something else. So it is called interrupt signal. So if this bit is set, that means it is the microprocessor is ready to accept the external interrupt. If it is clear, then it is, that means there is no interrupt can come here. It's okay? You do understand it now? Okay. What about the DF or directional flag? Directional flag is actually, direction flag is, you know, like this example also you are not will be clear right now. So if, for example, we have a many numbers in a memory location, which is called string operation. String means actually, you know, like string means like a set of data, like for example, the measure 1 grade of your class, of our this class, measure 1 grade. So we have a 26 student or 27 student. So 27 students. So for example, this is for one student, this data is for another student, this is the another student. So on until here, 27 students. So they are, this data, they are a set of data, and they are related to each other. And we save it, for example, with measure 1, with the name measure 1 in the memory. So what happens? So this is called the string. String means a set of data. When they are related to each other, they are put next to each other in the memory, and this is called the string. So this is string data. We'll see these cases in another chapter, but this is string data actually just simple examples. Then you will do. I mean, then I will go finish it here. So this string data, when actually we read them, we can read them from lower memory location to higher memory location, or from higher memory location to lower memory location. So directional flag means, you know, if it is set, look at here, if when set, when it is set, it means direction string data transfer or string data access happen from higher address to the lower address. Higher address to the lower. That means from higher address to the lower address. If this is happen if string that DF flag, directional flag is set. Otherwise, or if directional flag is reset, that means we can read the data, or we can access the data from lower memory location to the higher memory location. So this is actually related to the string cases. We will see it later. But right now, is it okay? Do you understand this one? That string data or a set of data, we can take them one by one from higher memory location to the lower memory location, or from lower memory location to the higher memory location. So it is then actually directional flag is is used. We can set it or we can reset it. Is that okay? Yeah. So and then there is another flag. It's called trap flag. So trap flag actually it is said when it is this flag is said, it allows the program to single step. It meaning to execute one instruction at a time and then jumps to the special service routine used for debug purpose. Like for example, like you know, like sometimes as I mean, if you can remember in a C program, for example, you have a somewhere your result is not expected one, something is different result. So you have to find where actually the problem is, where is the mistake in your program. So what actually we do, we can do one line by one line. first one line and then check the result is okay. If it is according to the expectation, then next line. So that means you can execute whole program at a time, or you can execute one line by one line. This is actually, we do it during the debug cases. So debug case means really to find the error cases. So during the debugging purpose, we actually use this step. So this flag is set. If this draft flag is set, that means it actually allows the program to single step execution. Single step, one line executed, and then see the result, show the result. Then second line, and then show the result. Something is like that. Is that okay? Do you understand this one? Okay, so that's all. So now what is the thing is we have these three flag. They are called control flag. So these three flag, IF, DF, and TF, interrupt flag, directional flag, they are related to the control operation. That's why they are called control flag. And other six, they are called the status flag. So overflow flag, sign flag, zero flag, auxiliary carry flag, parity flag, and auxiliary carry flag. So these are the six. They are called status flag, and all together is the flag bits. So this is all from this chapter. Okay. And there is another thing. Yeah, I think this is very basic thing. Like in memory is normally 8-bit memory, right, or 1 byte. So like if, for example, we have a number 0101, so that means it actually in one memory location, and then 00 it is in so this actually in memory, the number is all the information. Even if it is a data or instruction code, whatever it is actually saved as a binary information. But for our simplicity, with this binary information, we represent it in a hexadecimal. Like 0101 is 5, 0105, and 0000 is 0, and 0010 is 2. So we write it for our simplicity, but actually in a memory, the information is saved like that. Okay, and if it is, for example, this is the number 5502, 55 actually this is higher byte in higher memory location, and lower byte in lower memory location. Always look at here number. So for example, this memory location 00724, the next the top one is 00725, or whatever way. This way, when either moving forward or moving downward, doesn't matter. So this number is a matter. So that means, for example, if you write this one is 0074 here and 075, it's okay, it doesn't matter. But main thing is number. So higher memory, which one is higher memory location and which one is lower memory location? It's like that. Okay, so and then look at here, there is another example. Yeah, it's similar. So these are very basic information, I think. Okay, so for example, our number is 32-bit number. How can we save it? And start, so lower, it start from this memory location 00004. So definitely, so the lower 8-bit or lower byte is here, then next higher byte is here, then next higher byte is here, then next higher byte is here. It is like that. So it is called 32-bit 32-bit data. Like, you know, so this 8-bit. So then it will be 32-bit. So if it is in a binary, this one, so in a hexadecimal, we can write it here. And here is another example. That is symbol information. Okay, so that's all. I think here this is some basic information. So we are done in this chapter. So it is okay, right? So do you have any question here in this hardware hardware model of the microprocessor. All good. Okay, so let's see something more about. Okay, let me add another file. Sure. Okay, so I will discuss some, because we have already started the second experiment in the lab. So let us discuss some programs now. Okay, let's open this file. What is this? Okay, so let's do another one. Programming. Okay, so in the last lab, let's I discuss some information. I said you that in like in the lab is a complementary of the lecture class, and lecture is also complementary of the lab classes. So they are together actually. You cannot say that lab is lab. In some courses, lab actually I mean, the topics in the lab is not it's not coming in the lecture. During the exam or something, like they are kind of different, but here actually they are related to each other. So because lab is like a platform for practice, programming, like in the lecture we learn some programming, but how actually we practice them. So the lab is an opportunity, so something like that. So that's why I don't think separately, they are complementing each other. So that's why whenever something is discussed in the lab class, don't miss them. Actually it is from the lecture note, from the lab manual, but follow it actually. Note it down or highlight it on the lecture note or something like that. Don't leave it gone. Okay, so assembly language, I said, like languages are basically three types. We call programming languages, three: high level language, low level language, and machine language. So machine language, actually this is the language actually the machine or microprocessor or the computer system it understand. So this is called the machine language, and it is written as a string of binary 1 and 0. So it is written in a combination of 1010. Okay, so the machine language which computer understand without you. So this is the only language which the computer understand without using a translator program. So if we write our code in a machine language, that means it doesn't need any translator program, because it's already written in a right binary format. So this is the thing. So a machine language, so this but yeah, that's the simple information, but if you want to read more, you can read more. So basic thing is, machine language is a language written in a combination of 1 and 0. So what is the disadvantage here? So because it depends on machine, it is machine dependent. It differs from computer to computer, you know, like microprocessor to microprocessor, like what actually 8086 microprocessor support, it may not be supported by the iCore 7, Core i7 or Core i5, something like that. So definitely it machine dependent. It is difficult to program and write because, you know, it's very difficult. I mean, in a binary format to get, like, for example, you want to write what is the binary machine language for move AL comma BL, or move something like, or add x1 plus x1 comma x2 or something. These are the, what is the binary code for this one? It's very hard to find actually, but it is easy for us to write add x1 plus x1 comma x2, or c equal to a plus b in a for example in C language, something is like. So that's the thing. So that's why it is one of the disadvantages. It is difficult to write a program, and it is very likely to have error. It is prone to errors. It is difficult to modify. And also it is difficult to modify because if there is any mistake, it's difficult to correct it. All right. What about the assembly language? It is one of the low-level language. So low-level programming language that allows a user to write a program using alphanumeric mnemonic codes, you know, instead of numeric codes for a set of instruction. Like for example, we write move al comma 07, for example. So what does it mean actually, 07h? So it means this number is loaded on AL register. So here actually this instruction, you can see what are the things we use. We use alphabetic letter and numeric alphabetic character and numeric character. Like M is alphabetic character, M O V A L 07, they are the numeric character. So that's why it is called alphanumeric. And mnemonic codes, mnemonic actually, so this one is actually the opcode is called the mnemonic. Opcode is called the mnemonic codes instead of numeric codes for all instructions. So instead of this one, for example, the binary code for this one is B8, just for an example, 07, for example. This is the machine code or binary code for this instruction. So this one is the 07H. Yeah. So so this one is the 16-bit information binary code for this instruction. So it is not easy to find. I mean, this one, remember, or it is one to find B807, but it is easy for us to write this one. So here actually, okay. So, but what actually it needs here? We need a translator that actually translates this assembly language program to the machine language. It is called the assembler. You know, in the lab, what kind of assembler? What is the name of the assembler that we use in the lab? That actually helps to translate it, the assembly program to the machine language program. What assembler we use in the lab? No, it's not. Assembler. We use an assembler that actually translate our assembly language program to the machine language. Machine language and machine code or object code, this is the same that I said you in the lab class, the TASM. So TASM, turbo assembler. This is an so there are different types of assembler program available in the market, commercially available. One of the thing is TSM. So TSM is an assembler that we use in the lab that actually convert the assembly language into machine language or object file, you know, assembly file to the object file. So this is the thing actually. So object file is an example of machine language. So it is actually I mean the binary code for all the instruction, all the assembly language instruction. So assembler, that means main thing is we need an assembler or translator. It's called a translator also, that actually translate our assembly language program to the machine language program. So that's the thing. And what are the advantages here? We can say it is easy to understand and use. Okay, kind of. It is easy to locate and correct error because we can find where are the errors and we can correct it, and it is easy to modify. All right, but what are the disadvantages? It is also machine dependent, you know, like 8085, the previous version of 8086, it is not exactly same like the 8086 or the next version, like, you know, the assembly language what we can use for the microprocessor, recent microprocessor or microcontroller. You know, sometimes we can code our we can write our program in the microcontroller using the assembly language, but they are not fully same, kind of similar, a little bit, but you can do understand what does it mean, but they are not fully same. So that means it is kind of machine dependent. This is the disadvantage here, but it is easy for us to understand and use, and if there is a mistake we can find it, as you have seen in the lab, and we can correct it, we can modify it. That's all. Okay, so there is another okay, so in assembly language, basically in one line it can happen it can have something like we can put a label in a line, and we can have an opcode and we can have an operands. This is I already said you, and after semicolon we can write our comments, you know, like for example if we write move L, 07H. Okay, so you can put a semicolon here. So what does it mean? It means that move AL, 07H, and before that we put a we write some like L colon. So it means this is the label of this line. Like sometimes, you know, like we have to make a jump from one line to this line or anywhere. So we can just write a label. I mean something is followed with colon. That means it calls the label, you know. So label of this line. Okay. So and so then this is our main program. I mean the main assembly language program. So here actually we call this one, we have opcode and operand. So this one is called opcode or operational code. As I said you before in one class, that this is the main operation is identified by this one. So this is called opcode, and we can have two operands. This is first operand or destination operand, first operand or destination operand, and second one is the second operand or source operand. Sometimes it is called. So destination. So but first one is a destination operand. So that means yeah, this is called. So but in some instruction they may not have two operands, one operand. Like if you can remember multiplication, MUL BL. If we write MUL, BL, MUL BL, so what does it mean? It means AL multiply BL. AL multiply BL, and the result will be saved in AX. This is also I said you in one class that in multiplication and division cases, accumulator, this AL is a accumulator, 8-bit accumulator. AX also a 16-bit accumulator. Accumulator is by default, when a first operand is accumulator. It's always. So that means so operand can be 1, can be 2, mostly 2, but some cases it may have 1 operand. In some cases also there is no operand. We'll see. Okay, so this is and what about the after the semicolon? After the semicolon, it is called comments. So this is also not part of the program. We can write something like, what does this line mean? For example, we move AL, 07H. What does it mean? So load 07H to AL. So that means AL will be now, after this instruction, AL will be 07H. Something like. So you can write, put some, sometimes you can put some comment in some line using semicolon. It's up to you, but it is not important, big issue. It is not part of the program. Okay, so these are the things, and this is called like that. So okay, and also I said you there are 2 operands. Like first one is like, for example, add AX comma BX. What does it mean? It means, and before that we put something followed, something is followed with colon. So it means this is the label of this line. And add AX comma BX, that means AX plus BX, AX content and BX content, they will be add up, destination index and source index. No, there is nothing source index and destination index. It should, they are SI and DI. DI for destination index register and SI for source index register. So AX content and BX content, they will be add up and result will be saved in AX, because this is the destination operand, I said. Okay, so our first operand, result will always move to the first operand. That means there will be no change in BX. So for example, AX is AX equal, for example, 2 0 1 0 H. Okay, and BX is BX 3 0 6 2 H. Just for an example, if we have the instruction add AX comma BX, that means these two will be add up, and what will be the result? It will be 2 7 0 5 H. Okay, so that means this result will be saved where? Where the result will be saved? In AX. So that means AX will be now change. AX will be, the AX data is overwritten. The previous data was 2010. Now it will be overwritten with 5072H. Is it okay? But there is no change in BX, because BX is not, we do not put it in the first operand. Is that okay? Do you understand this one? The first is the destination operand, second is the source. Always, yes, always. Okay, so now, okay, let us go to the high level language. There is another language called high level, like C program, C language actually, you use it. But there are many other languages that they are called high level language, like Fortran and then COBOL. So this one was the first high level language, but there are many languages we use nowadays. Like C is one of the great example. Java, these are the things. So they are high level. Also Python, and many other things are there. So they are high level language, but they are very friendly compared to the low level language like assembly language. They are more friendly, but problem is, it needs a translator. Again, it needs a translator, or it's called a compiler. It's called a compiler that actually perform the translating operation, that actually translate high level language to the machine language. Okay, so this is called the compiler. So basically, for example, this is our source code or C programming language. So translator actually convert it to the object code or binary code. That's the thing. So yeah, so that means yeah, using it. So in the middle, so this translator is called compiler here. For the high level language, it is called the compiler, and for the assembly language, low level like assembly language, it is called the assembler. Okay, so is it okay, clear? Yeah. So, and we can see some some example here. So now this is our main theme. Okay, so addressing mode. What are the Okay, so before addressing mode, I'll discuss something that actually I also discuss in the lab, that programming method. Assembly language, actually how many ways actually we can write our program. We can write basically two ways. One is called full segment definition from, and one is called simplified segment definition from. So simplified segment definition from, actually I discussed in the lab, that as we don't have long time in the lab, so that's why just only we practice the simplified segment definition from, but we can write it in a full segment definition from. We'll see it if possible. And then what are the other information? There are in our program we have two types of instruction. What does it mean? One is called real instruction and one is called pseudo instruction or directives. So what is real instruction and what is pseudo instruction? So like, for example, if you can remember, in our program, we write title, TITLE. This is not part of the program. Title, TITLE. We write title and then we put something. So this is not part of the program. If for example, we write something with the name title, so this is not part of the program. This is not the real program. It's not important info. But if there is any mistake, it actually show you the error message. So that means this is not the real instruction. This is the pseudo instruction. So, and also, can you remember we use something like x1 db, and then we put like 34h, for example. And then we also end at the last of the program, we also write END. So these are the things, kind of some example, like title, DB, and end. So these are the things actually not part of the program. I mean, they're not part of the, I mean, they are not the important part of the program. I mean, so even without this thing, can you remember in a hex code, when actually we check the binary code in a hex format, comment is totally different thing. Comment is definitely not part of the program, but something we can write as a part of the program, but they are not the real instruction. They are called pseudo instruction or directives, like title, DB, END, something like that. And then dot data, dot code. These are the things. If you can remember, when we check the check the program in a memory information, we check that the lines, what are the real instruction, they are shown there with a machine code. So, but these are the things. There is no machine code for title. There is no machine code for end. There is no machine code for DB, X1. These are the things are not there. So what so that means some instruction, in our program, some instruction we write them, they are machine real instruction, and after converting to the machine code, they have the machine. Main thing is all the instruction that is translated into a machine code, they are the real instruction, main thing. But pseudo instruction, they are not translated in the machine code. They are just used as a direction, or just for making the things more understandable or more user friendly. That's the thing. So look at here, real instruction such as move, add, are the real instruction. They are translated by the assembler into machine code for execution by the CPU. But pseudo instruction, on the other hand, do not generate machine code, are only used to give directions to the assembler about how it should translate the assembly language into machine. So they are used kind of like an directives, directions. So they are using I mean, so but main thing is they do not generate machine code. Okay, so that means there is no machine code for end, there is no machine code for title. These are the things. Okay, and now how actually we write our program? First of all, we open a notepad. So it is so, and then we save it as a ASM file, .asm file. Then we use using the assembler, like we use the TASM, TASM. We use the TASM that actually translates this assembly language file into machine language file, or this is called the object file as well. So then we use a linker. What kind of linker we use in the lab? T-link. We use the T-link that actually convert this object file, that actually convert this object file into two more files. One is called exe file and one is called the map file. So I said in the lab that map file is related to the memory profile, like what part of the memory is for code segment, what is for stack segment, what is for data segment, something like that. And exe file, this is our main file that is used to check the result. Okay, so this is the thing. I already discussed something in the lab. Okay, now in actually the program template, we said there are two ways actually we write our program. One is called full segment definition from, one is simplified segment definition from. So full segment definition from, actually what actually we do, we for every segment, like code segment, data segment, stack segment, so every segment we put a label and segment, and then label ends. This is, and in the middle we write our the lines related to that segment. So that means label and segment. Label ends, END. We use END, but we do never use ENDS. S for segment here. So let's have a look. So like for example, at the beginning we write the title. Title is same as like a simplified segment, also we use some title. And then we like for the stack segment, we write the name. The label is like, for example, HTSEG. You can write any name. And then we write segment. So like ST or STSEG segment, and then we write something here like DB64 DUP. What does it mean? I will explain it later. So and then we write the same name here, what is written at the begin and ends. That means, so this is the beginning line of the stack segment, and this is the finishing line of the stack segment. So it starts with and this name is anything. It can be like, for example, you write ST for a stack segment, or STSEG, whatever, it's up to you. Like here it is written STSEG. So this is okay. You do understand this one? And look at here for data segment. Look, but what actually we write in a simplified segment? We just like dot stack. You can remember, we just write dot stack. STACK. So instead, so what is written in a simplified segment, like the segment stack segment is defined just like a dot stack, but here it is a name with written segment and name with written ends. So just only that, this is the difference. Again, for the data segment, we look at here, we what actually in a simplified model we use it, we write it dot data, right? In a simplified model, dot data. But what is written in a full segment definition format, we write a name, and then segment, and then we write in the middle, we put our data information, and then we write the same name with ends. So that means this is the beginning of data segment, and this is the end of the data segment, and in the middle we have the data. And this name, it's up to you what name actually you write for the data segment. And then in the code segment, look at here, this is also name of the code segment, and this is the end of the code segment here, end of the code segment. So name and ends, name and segment. And what else is, what is the difference here also? The difference here, in the first line in the code segment, we write the name that we use for the stack segment, code segment, and data segment. We have to declare it here. Assume with the writing, assume CS for code segment, so CS colon CD SEG, the name of the code segment. Then comma DS colon DT SEG, the name of the data segment. And then stack segment, the name of the stack segment, SS colon, the name of the stack that actually you put here. And then initialize the next two line is for initializing the data segment. What actually we wrote in the lab for initialize the data segment, we write it little bit different way. Move AX, comma, @ data, right? Can you remember? @ data. We write it in a simplified model. @ data, and then move ds, x. So what is written here? Move ax, not @ data. Move ax, dt data segment, the DTSCG, the name what actually you wrote here, DTSCG, and then move ds, x. So this, and then all the information, and then this two line is fixed, same like in it. So there is no difference. Is it okay? Do you get it now? What is the difference in a full segment definition from and simplified segment definition from? The difference is clear here. So next lab we write our program in a full segment. So this is not the main issue. Either you write in a simplified model or full segment model. This is not a big issue. Big issue is writing our program. That's the thing. So, but just for understanding that two ways we can write it, just for here. So that means next lab we will write the programs in this way, so that actually it will be clear. But later on, actually, we will again, because this, it needs more time to write more lines. But later on, actually, we'll write mostly in a simplified model. Okay. So this is full segment model, and there is another thing is called a simplified model. So you remember, if you look there, you can see that a dot model, we write it dot model is small and dot stack, and inside the dot stack, so that means as a stack segment we can allocate some memory, like for example 64. If we write 64, that is 64 memory location. If you write 64H, 64 in a decimal, if you do not write anything. But if you write 64H, that means in a hexadecimal 64. Or you can write anything, 10, 20, 30, or 15, just few memory location for a stack. And then dot data, this is for our data segment. And then dot code, inside there we have data segment, code segment. So, and first two line, you can see first two line is for initialize the data segment, move AX comma at the rate data, move DS comma S. It's not fully same as like a full segment, but kind of similar. And we have some two lines there in the lab. And what is, I said in the lab that dot model is small. It can be small model, it can be medium model, it can be compact model. The small model is here. This is one of the most widely used memory models for assembly language, and it is sufficient for most programs. The small model uses a maximum of 64 kilobyte of memory for code and another 64 kilobyte for data. Okay, so this is, we already know it. So 64 kilobyte for code segment and 64 kilobyte for data segment. But medium model is, you know, if data segment, the data segment must fit into the 64 kilobyte, but the code segment can extend more than 64 kilobyte. What is in compact model? This is opposite the medium. So that means code segment must be fit to the 64 kilobyte, but data segment can be more than 64K. And what is the large model? Combining the two preceding, so medium and large. So that means data segment is more than 64 kilobyte and code segment also more than 64 kilobyte. If this is the case, then it is, we have to write more dot model large. But mostly dot model is small model is enough. It's okay? Do you understand this thing? Clear? Is it clear? Yeah. And what else? Yeah, defining this different segment like stack segment, data segment, code segment. We just simply use dot code, dot data, dot stack instead of writing, you know, a name with segment, name with ends. You know, these are the pseudo instruction. We use them in a full segment definition model, but we don't have to write them like that way. Yeah, so this is the simplified model already we use in the lab. Okay, now what is called pseudo instruction? I already said. I mean, there's these are the instruction we use them for as a like directives, and they are not converted to the machine code. They are just for used for direction purpose, something like. So what are the things? One of the thing we use it like DB. So define byte. So define byte means define byte. So like for example, we have 5 data. FFH 5 data. So we can write with a directive like DB define byte. So that means each one is saved in the memory, taking one memory location or 1 byte. Okay, so this one is this number is okay. Just look at the memory. For example, this is the memory, and if we write, for example, x1 dB, and then instead of like, you know, in the lab you use one number, we can assign many numbers with a variable. So it means actually x1 dB. If what does it mean? X1 dB, and then we have, for example, here 5 number. So that means this 5 number is assigned to a this 5 number is assigned to a, they are string variable x1 assigned to a string variable x1, and they are saved in the memory as a byte. DB defined byte as a byte. So like for example, is this one is E, and definitely in a H, sorry, FF, then FF, and then one more FF. Okay, something like that. So it be, and then first, so with the variable name x1, and it is with the name x1. So under the x1, we have a so x1 is a string variable, because, and they are a set of data. A5 data or a set of data is assigned to a string variable x1. Okay, and each one is taking one memory location or 1 byte. So that's the defined byte. But if we write define word DWO, it means define word. So that means each one will take 2 memory location. So that means F7. So 00 higher byte will be 00, something like that. If we write DWO, it means define one. Okay. And then like, okay, so this one actually you can see in an example, DB64 dupe, dupe, and then a question mark. So it means actually 64, I mean 64 memory location, 64 memory location. It means that 64 duplicate memory location, it to do the duplicate operation, or dupe is for duplicate, or same thing. So 64 and question mark, you know, question mark is for empty, keeping it empty. This is you already use it in the lab. So that means 64 memory location, it reserves and they are empty. All right. So 64 memory location it reserves as an empty. So look at this judo instruction. This is a kind of, this judo instruction reserves 64 memory location or 64 bytes of memory for a stack, because this one we used it in the stack segment. That's why. So dot stack, and then if we write DB64 du question mark, it means memory location they keep it empty. Question mark is for empty. Is it okay? Do you understand this one? And then you also have seen that assume also in a full segment definition format. This one is also kind of judo instruction. They are used. This is also like, you know, we use it, and then also we use it end judo instruction. It is the instruction ends the entire program, and then we use like move ax comma DTSCG, or move ax comma at the rate data in a simplified model. So what does it and then move ds comma ax. What is the purpose of this two line? I said in the lab, or also here also, it is to initialize the data segment. Initialize. So data segment must be initialized by the program writing this two line. So in a full segment definition format, we write ax comma the name of the data segment like DTSCG, or we can write in a simplified model move ax comma at the rate data. And also we write this two line at the end. What is the purpose of it? To return the control to the operating system. So as I said you that sometimes we use the Windows, we write we use some program in a Windows mode, we use some program in a DOS mode. So just shifting the control from one different operating. Otherwise, if you do not write it, it will say illegal termination or something like that. Okay, so sometimes we use like, you know, some judo instruction, it is called org for origin or beginning of something. This is for, we'll use more example. And DB for defined byte. The DB judo instruction is the only most widely used data judo instruction in assembler. It allows allocation of memory in byte size, as I said you know, byte size or 8-bit. This is the smallest allocation unit permits, and DB can be used to define numbers in a decimal, hexadecimal, or as ASCII code. Okay, look at here. For example, A1 DB25. That means 25 is a decimal number. So 25 decimal number is assigned to a variable that is saved in the memory with the name A1. Okay. 25 is a decimal number, but if we write A1 DB 10001 and then B, so that means this is the binary number. This binary 8-bit number is assigned to A2. And A3 DB 12H, it means it's hexadecimal number. And if we write ORG, this one, it means the it means that next variable, it will take the memory location, start from 10H, like, you know, for example, we have some memory location here. So here it is DS. For example, this one is the beginning address of DS colon 00 and DS colon 10. This one. Okay, so normally if we do not mention anything ORG using something ORG, so it start from the beginning address, base address to it start from base address to onwards, saving the data. Okay, but if we use like ORG10H, that means it start from this address with offset 10H, from start from here. You get my point? If we write a ORG10H, it means it starts saving the program, saving the data from this location, the location with offset 10H. And then if, for example, ORG10H, and then next one is like A4DB name with a quotation mark, single quotation or double quotation mark. It means this is the ASCII character, ASCII code. You know, can you remember in a number system ASCII code? So that means what is the ASCII code for N? It will be saved here, capital N. And what is the ASCII code for A? It will be saved here. And what is the ASCII code for M, small m? It will be saved here. And what is the ASCII code for a small e? It will be saved here. Something is like that. And so so that the name of this string, this is also string character, string variable, string, it will be A4. So the name will be A4. Do you get it now? Is it okay? What is the use of ORG10H? Yeah, ORG means the beginning. So it's, if we do not use it, that means it actually start from the base address 00 offset, 00 offset. But if we use like ORG10H, it means it start from the memory location with that offset. This is the big. And then our data, it can be decimal number. We can declare it as in a decimal number. We can declare it in a binary number, hexadecimal number, or ASCII data. But everything is converted in a binary code, in a memory, right? That's it. And we can assign a variable to this number. I mean, actually the number, and they are in a, we can assign a variable to the number that is saved in the memory. Okay. Then DUP for, I said already, DUP for duplicate. If we do the same thing, same type of data, then we can use DUP. Like for example, if we use like array1, DB, FF. So why actually we use 0? FF is enough, 8-bit, but why actually use 0 here? If MSB bit is a character hexadecimal, like A, B, C, D, E, F. These are the character data, right? And 0 to 9, they are the numeric data. If MSB bit is a character data in a hexadecimal format, then we must use 0. But otherwise we don't. Like for example, if we have for example 2F, this is the 2FH hexadecimal number, 2FH. So MSB bit is a numeric data. We don't have to use 0 here. But if it is like AFH, so what is the MSB bit? MSB bit is A. So if this is a character data, character digit. So we have to put a 0 here. We don't have to put 0 here. If it is a numeric, MSB bit is a numeric. Is it okay? Do you understand this one? Otherwise, actually, computer will show some error. So, this is 0 is nothing but FF. So, if, for example, we have a 6 data. Instead of 6, we can use it like that way. The array 2 dB. dB is for defined by, and 6 DUP, and then this one. So that means what this one will do the same thing, same purpose as this one. So that actually instead of, we don't have to write this number because they are same number, so we don't have to write 6 times. We can write 6 DUP, duplicate this one. Okay, it's okay. You do understand this one? Okay, all right. And then okay, that's good. Yeah. Okay, then we can write also this one like org, for example, org 50, and then we have an array 3 dB 64 DUP question mark. So what does it mean? So it means, you know, org, I said just a few seconds back, I mentioned that org, what does it mean? So it means actually it start from 50, it start from a memory location with offset 50H, and then it takes 64 memory location, 64 byte size memory, or 64 memory, because each memory location is 1 byte. So 64 memory location, it reserves empty. So question mark means the number is empty. 64 memory location empty with the name array3. Is it okay? Do you understand this one? So I mean, from this memory, from the memory, it starts from the I mean, from memory location with offset 50H, it reserves 64 memory location with the name A3 and empty memory location. Question mark is empty memory location. Okay, but if we do not have any name, that means it reserves 20 memory location space without initialization. So there is no initialization. Without initialization, okay, without initialization, I mean, reserve empty space without any, or there is no number, just empty. Okay, but if we write like this one, it reserves 20 bytes of memory location and fill it with number 10s. Okay, these are the things. And then DW for defined word, like if we have our data is word size like 30 instead of 16-bit, if they are 32-bit, sorry, 32-bit, yes, like that. So we normally use them in a word. So it's like that, and or 16-bit or something like. Okay, this is same thing. Okay, there is another example of pseudo instruction. It's called EQ, equal, for equate or equal. Okay, so like for example, count EQ 20 or X EQ 20. What does it mean? It is the same as like count equal 20. They both are same. So what is actually, so we can use EQ or we can use the equal sign. But what is the difference of this one with X? I mean, or we can write, for example, count DB 20. What is the difference between these two? One is count EQ 20 or count equal 20, and another one is count DB 20. What does it mean? They are quite similar, but what is the difference is that this one is not saved in the, okay, let me, so this means that 20 is initialized to a variable count that is not saved in the memory, but this one is saved in the memory. This one is saved in the memory with the initialization, that 20 is initialized to count variable. Here we also use variable, but it is not saved in the memory. That's the difference. So look at here, EQ without, look at here, without occupying a memory location. Without occupying memory. So EQ doesn't set aside storage for a data item. Same thing. Okay, now what else we can see here? So here are a few more examples. You can see if we have use a quotation mark like single quotation or double, it means it is a ASCII code. We have to look at the ASCII code for this character data, and that's all. Here is a few examples. Now it's about the let us open the programming files. Then I will. Okay, so now as we started programming in the first lab, first exercise, we use it very simple one, like we have two number, they are in memory, and we add them together and we save the result in another memory location. So, but you know, like if we have not two number, we have many number. We have many number, so how can we use them, we add them together? For example, look at here this program, like sum of a series of 10 numbers and store result in memory location. So if you look at here, you can see that, for example, the list or data, we name it a list db, we random 10 number, for example 2 34 56 70, it's like it's 10 numbers. Okay, so with the name, so we put them in a memory location, so they are string data, and the variable is list. So that means what it means that in a data segment we put them here in a 10 data. So like a 10 data, we put them in a memory location, and with the name list. So list is assigning the first location, list colon, and we have a 12 here, 12 here, and then 34 here, and then last one is 36 here. Okay, and we take another memory location, we reserve another memory location, it is empty and its name is total, for example, or result or sum or whatever it is, total, for example, total here. Is it okay? Do you understand this one? We have the 10 data, we take them one by one and we will add them together. Okay, and we add them together and we keep it here. So 2 is easy, right? But how we have a set of data, not 2 only. We have a 10 data, 100 data, something like that. Okay. So like what actually we do, and also you know one thing is you can say, I said you that we have to assign also dot stack segment. So dot stack, this is actually, if we avoid it, it will show some error. So you can use also declare dot stack and some memory location like say 60 or 10, for example, some memory location assigned as a stack also. And total db question mark. So question mark means it is empty without initialization. Okay, and now dot code, under the dot code we write these two lines to initialize the data segment. It is very same everywhere. And then we can use, so we can use the loop instruction, because you know, like loop, we can use the loop and we set a counter, move cx comma 10. It means say we set a counter with 10 because we have a 10 data. Okay, so and then what actually do, move si comma offset move si is a, you know, source index register. Can you remember source index register si? The use here, move si comma offset list. What does it mean? List actually I mean it's identifying the first memory location of this data set. So offset, it means si actually, si equal, what does it mean? Si becomes the offset address of the first memory location. It may be normally, if it is start from 0 0, then it means si is 0 0 0 0 h, for example, if it is the base address. Okay, Si becomes 0, 0, 0, H. Now I said move al comma 0 at the beginning. If we add a big number, I mean many numbers, so beginning the sum is 0. For example, move al comma 0. Then at al comma square bracket si. Square bracket si means square bracket means memory location. So it means al comma memory location data. What is the offset of that data? 0, 0, 0, 0, H. The offset of that data. So 0, 0, 0, H or square bracket si, it means that the memory location data, so the memory location with offset 0, 0, 0, H, that data will be added with AL and result will be saved in AL. So what is the data in 0, 0, H offset? It's 12. So that means AL comma 12. AL at the beginning we initialize is 0. Now 0 plus 12 is 12. Then we increment SI. That means SI will be one more, one adder. That means 0, 0, 0, 0. Sorry, 0, 0, 0, 1. SI will be 0, 0, 0, 1 here. It will be 0, 0, 0, 1. And then loop back. We back means here. We are back. Back. What is the label of this line? Back. This line back. You can write whatever you want. Like you can write L. You can write repeat. Whatever you want. So just it comes here. It comes here, and now then again it will do at al comma square bracket si. Now what is the si? Si is not 0, 0, 0, 0 anymore. Si has become 0, 0, 0, 1. So it will take this data 34 at al comma al. What was the al value? 12 plus 34. Now second number, then increment si. So you will loop again. So how many times the loop continue? 10 times, because we set a counter 10. And we have a, why actually 10? Because we have a data list, we have a set of data 10. So that's why we put a counter 10. And this is the loop example. And then so finally, once so every time counter will be one decrement, 10, 9, 8, so on. So that means 10 times the loop continue. So once it is done, then it will not continue this loop anymore. Then it will come out this line. So what actually we do, move total comma AL, because our result is always saved in the AL. So total comma AL means what is total? Total is the name of this memory location. So it will go to memory location and then end. Is it okay? Do you understand this one? If we have a set of data, how can we use it? We can use like the simple method that we use in the lab. We can, we can use a loop instruction, and the many data. Yeah, is it okay? Do you understand this one? I cannot see the message. I mean, maybe the system is a little bit hanged. System is a little bit hanged here. Hi guys, are you there? So I actually it becomes, yeah, it becomes freeze actually from my side. That's why actually I don't know. It's happened almost every day. Like end of the, I mean, close to the end of the lecture, it becomes freeze. And yeah, so I don't know. It's same thing happened today also. So anyway, so hopefully it is okay, right? The example that I said here, like if we have a series of data, how can we use it? We can use an index register. One of the thing is we can use an index register like SI index register, and we can use a loop instruction. Okay, without loop also we can do it, like I mean something else, but loop is, I mean, makes it easy. But is it clear, this program series of uh, if we have a series of data, how can we add them together? Is it clear? Okay, and then actually in the lab, actually, I think you can let me check. Okay, maybe the report, you can hold on the report, so no need to submit it tomorrow. So I will discuss something more, and then together you will submit it on the web report. Okay, so yeah, okay, so so time is up. So okay, so do you have any questions so far? Do you have any question here until now? Okay. Okay, so tomorrow, inshallah. So tomorrow in the lab class, we'll discuss more. Yes, yeah. Okay. Any comments from Abdullahi? Okay, so if you have any comments, you can turn on your microphone and then tell me. Okay.
Victor, the last
Yes.
page of homework, do we solve all question or just first two?
Which one?
The homework.
Homework 1.
Yes.
Homework 1, yeah, all the things. I mean, yes, homework, all the things. Yeah, most of the things is just one line. I mean, the later part is very basic. It's about, like, you know, yeah, finding the offset or finding the physical address. If offset is this one, something is like that. It's very basic thing. So
But
huh?
the last page, there is, I guess, 5 questions. Just to the number appear. The last 3 were erased by you.
It doesn't matter actually. Don't worry about the number. Just I mean, write the answer. That's it.
Okay, thank you, Doctor.
Okay. Okay. All right. Okay. Inshallah. Any other question? Okay. So yeah. Okay. See you in the next class, inshallah, and tomorrow also as well. Okay.